Welcome to the Total Station Math tutorial. My name is Jason Taylor and I will be your instructor. As a red seal carpenter for more than 20 years, I learned from experience that interpreting drawings and accurate measurement and layouts creates carpenters that are in demand in the construction industry. Being in demand is what it's all about, and that's what I'm here for, to make you in demand. Designers, architects, and engineers are creating more and more challenging, complicated, and complex structures. So precise layout and measurements are essential to accurate builds. And avoiding costly rework and ensuring productivity and future work for UBC members. The Total Station is a powerful layout tool, combining a transit, electronic distance measurement, and an onboard computer. So the carpenter has an incredibly accurate and a versatile tool to perform difficult or complex layout challenges. Math is a part of everything we do daily as a carpenter and a UBC member. Every time we use our tape measure, we're using math. Using a Total Station is really not that much different, but we need to understand a few math concepts before we can use this tool accurately and effectively. The math for Total Station is straightforward. Beginning with a review of decimals and fractions, we will move on to elevations, including a review of backsight, height of instrument, and foresight. From there, we will examine degrees, minutes, seconds, and decimal degrees. We will review azimuth and bearings, as well as subtracting and adding angles. Lastly, we will review 3, 4, and 5, identifying the angle of interest, opposite and adjacent sides, and a hypotenuse of a triangle, and how this relates to the tangent of an angle. At first, this may seem daunting and intimidating, but we're going to take this step by step. Remember, the skills added by training on a Total Station is immeasurable to your skill set and employability. That's what it's all about. So congratulations on your dedication to training and improving your skills and making Local 27 and the UBC strong. We're going to start off at the basics. I'm going to teach you how to convert feet, inches, and fractions to decimals. The reason we need to do this is because on a set of prints, everything's given to us in feet, inches, and fractions, but to punch it into a calculator, we need to get everything to decimals. So to start out, we're going to go from feet, inches, and fractions to decimal feet. Okay, so to start out, we'll start out with 12 foot 8 and 3/16 of an inch. Anytime we're given feet, inches, and fractions in this form here and we want to turn to decimal, we're always working from right to left. So we've got the 3/16 of an inch. So to work that out, we're gonna go 3 divided by 16 in our calculator. So 3 divided by 16 equals 0.1875 inch. The next step, we're going to add our full inches to it. So we've got 8 full inches, so we'll be plus 8 inch equals 8.1875 inch. Next step, we want to convert that to decimal feet. So to do that, we're going to divide by 12. We have 12 inches in a foot, so if we divide the 8.1875 by 12, that's going to give us our number in decimal feet. So we'll be 8.1875 divided by 12 equals 0.6823 feet. This step right here is where a lot of students go wrong. I see a lot of people multiplying by 12 by an accident, and then you're ending up with a huge number right here. We know that 8.1875 inch is less than a foot, so this number here has got to be less than 1. So if you multiply by an accident, you end up with that huge number. Just take a step back, divide by 12, and you'll come up with the right answer. Last step, we're going to add our whole feet to it, which we said was 12 foot. So our final answer will be 12.6823 feet. I'm going to throw another one up on the board here. I find a lot of students getting tricked up on this one here. 23 foot 0 and 7/8 of an inch. So again, we're going to start from the right. We're going to get rid of that fraction. 7 divided by 8 equals 0.875 inch. Okay, what students do is they see this number here. It's already less than 1, and they automatically add the 23 to it, getting 23.875. If you do that, you're getting 23 feet and 0.875 of an inch. It doesn't make sense. So the step that students forget at this point here is to divide by 12. Okay, so remember we're in inches. We want to convert to feet, so we still have to do that step by dividing by 12. So we 0.875 divided by 12 equals 0.07 29 feet. And then the last step now will be to add the 23 feet to it. So plus 23 feet equals 23.0729 feet. Okay, so that would be our final answer there. We're going to go back the other way. We're going to go from decimal feet to feet, inches, and fractions. Okay, so we could have a number like 15.3785 feet, and we want to convert that into feet, inches, and fractions. So right off the bat, we've got 15 whole feet here. So I'm going to record that, 15 foot. We're going to take that out of the equation, so we're going to go minus 15 equals 0.3785 feet. And now we want to convert that into inches. We've got 12 inches in a foot, so we're going to multiply by 12 equals, so 0.3785 times 12 equals 4.542, and now we're in inches. So 4.542 inches. We've got 4 full inches. So we'll record that. We're going to take that out of the equation. So minus 4 equals 0.542 inches. And now the last step is to get it to the nearest 16th of an inch. So in order to do that, we're going to go times 16. Okay, the reason we multiply by 16 is because 16 over 16 equals 1. So by multiplying this number here times 1, we're not changing the number, but this way here we'll be getting into a fraction over 16. So we're going to go 0.542 times 16 equals, and we've got 8.672 over 16 of an inch. And we're going to round it to the nearest 16th of an inch. So because this number here is more than 0.5, we're going to round up to 9/16. And we'll record that number over here, and we would have 15 foot 4 and 9/16 of an inch. Okay, so just to do one extra one here for practice, we can throw another number up on the board here. Let's say we've got 57.8394 feet. We're going to go through the exact same steps. We've already got our 57 full feet, so we'll record that. We're going to subtract that out of the equation. Minus 57 feet equals 0.8394. We said we have 12 inches in a foot, so we're going to multiply that by 12 to get it into inches. So we're going to be 0.8394 times 12 equals 10.0728 inches. Next step, we want to get, we've got our full 10 inches there, so we can record that. Okay, we're going to minus the 10 inch equals 0.0728 inch. And now we want to convert that into fractions. Again, we're going to multiply that by 16 to get it to the nearest 16th. So 0.0728 times 16 equals 1.1648 over 16. We're going to round that to the nearest 16th. So we've got 1/16 of an inch. So our final answer would be 57 foot 10 and 1/16 of an inch. So those are the steps that we're going to take to go from feet, inches, and fractions to decimal, and from decimal to feet, inches, and fractions. The next concept that we have to review is benchmark, backsight, height of instrument, and foresight. With a firm grasp of these concepts, we can shoot elevations of footings, floors, walls, caissons, piles, and other components. A benchmark is a given point of elevation from which all other building elevations are shot. It can be a true elevation based on distance above sea level, or an arbitrary elevation set by a survey team, at, for example, 100 foot. Generally, the benchmark is established by a survey team before construction begins. It can be a nail set in a concrete sidewalk, a point on the side of an adjacent building, or a stake driven in the ground. From this established point, we can shoot all of the elevations of a construction project. Okay, so we're going to start off with a benchmark of 100 foot. We'll call that above sea level. Okay, what we're trying to do is locate and lay out the top of our foundation wall, and we'll say we're given a height of 102 foot. Okay, so somewhere on the job site, we're going to set up our instrument. Once we set that instrument up and level it out, the whole concept of this thing is that we're shooting a horizontal line level across the entire job site. Okay, so what we need to do is we need to reference the height of our instrument, call that our HI. I'll figure out how to determine that in 1 minute, and then we're going to find the difference of the height of instrument down to that foundation wall to determine the height of it. So we got our 100 foot above sea level. First thing we're going to do is we're going to have to get a measurement using our rod to determine our height of instrument. So we take our instrument, we shoot back at our given point, we're calling our benchmark. This shot back here we call our back sight. Okay, so if we have our rod here, we'll keep the number simple here. We'll say the distance from our benchmark up to our instrument here is, let's call it 5 foot. Okay, that's our back sight. So we take our benchmark of 100 foot. Okay, we're going to add our back sight, which is 5 foot, and it's going to equal 105.00 foot, and that's going to be our height of instrument. So that means the elevation of this line all the way across here is 105 foot. From there, we're going to take the instrument and we're going to shoot it in the direction of our foundation wall. And we're going to get, what we're looking for is a distance from our height of instrument down to our foundation wall. Okay, this is called our foresight. Okay, which is what we're looking for. So if we have 105 foot height of instrument, we're going to subtract our 102 foot from our foundation wall. So it'll be 105 foot height of instrument minus our 102 foot elevation. And we'll get 105 foot minus 102 foot would be 3 foot, would be our foresight. So the distance from here to here would be 3 foot. So we could measure down from our height of instrument down the 3 foot, and we'd be at the top of our foundation wall. So that's the steps we go through to determine the height of our foundation wall. Next up, we're going to figure out how to convert decimal degrees to degrees, minutes, and seconds. The reason we need to do this is on drawings, a lot of the time our angles are given to us in decimal, but to get it into the total station, we need to convert it to degrees, minutes, and seconds. Okay, so let's use the number 275.4824 degrees. And we're going to convert that to degrees, minutes, and seconds. The way I think of it is it's very similar what we did earlier from converting decimal feet to feet, inches, and fractions, where we used the number 12 and we multiplied by 12 because we had 12 inches in a foot. With this one here, we've got 360 degrees in a circle, we've got 60 minutes in a degree, and 60 seconds in a minute. So the number we're going to be multiplying this time is going to be by 60. So we've got 275.4824 degrees. Okay, we can take the 275 out because we know that we have 275 degrees, and we're going to convert this number here to minutes and seconds. So we'll take the 275 degrees, we're going to be left with 0.4824 degrees. Now we want to convert that into minutes, so we're going to multiply by 60 because we have 60 minutes in a degree. So we're going to go 0.4824 times 60 equals 28.944, and now we're in minutes. Okay, the symbol for degree is just a little circle. The symbol for minutes is the same as the symbol for feet. We've got 28 full minutes there, so we can record that. We have 275 degrees, 28 minutes. We're going to take 28 out of the equation there. Equals 0.944 minutes. We said we have 60 seconds in a minute, so we're going to multiply by 60. And we've got 56.64, and the symbol for seconds is the same as inch. Okay, any instrument I've always used always rounds to the nearest 5 seconds or 10 seconds. For us, we'll just round to the nearest 1 second. So the nearest second there, we're 0.5 or higher on the right side of the decimal here, so we'd be 57 seconds. So we'd have 275 degrees, 28 minutes, and 57 seconds. Okay, so we'll do another example here. This time we're going to go from degrees, minutes, and seconds to decimal degrees. Okay, so we could be given a number like 57 degrees, 38 minutes, and 15 seconds. So to convert the 15 seconds into decimal, we're going to have to divide by 60. So we'll take the 15 seconds, we're going to divide by 60, equals 0.25. Okay, now we divided the seconds by the 60, so now we're in minutes. 0.25 minutes. We're going to add the 38 whole minutes to that number, so plus 38 minutes equals 38.25 minutes. And then we're going to take that number and we're going to divide by 60 again to turn that into degrees. So we're going to divide by 60 equals 0.6375 degrees. We'll add our full degrees to that number, 57. So plus 57 degrees equals 57.6375 degrees. Okay, so our final number there would be 57.6375 degrees. Okay, next up, we're going to add and subtract degrees, minutes, and seconds. Okay, so we can start off with any number here under 360 degrees. Let's say we go 105 degrees, 14 minutes, and 33 seconds. And we'll add, let's say we go 52 degrees, 20 minutes, and 15 seconds. Okay, we're gonna set it up just like a normal adding question where we've got everything lined up properly. We've got the minutes, or the seconds here above each other, the minutes above each other, and the degrees above each other. And it's just gonna be straight math. So we can go 5 plus 3 is 8, 3 plus 1 is 4, so we got 48 seconds. Over here we've got 14 plus 20 is gonna be 34 minutes. And over here we've got 157 degrees. Okay, pretty straightforward, but a trickier question would be when you get some bigger numbers. Say we got the 105 degrees, let's go 28 minutes and 38 seconds. And let's say here we've got 114 degrees, let's go 42 minutes and 29 seconds. Okay, so now what we're going to do is we're going to add these two numbers up. We're going to go 38 plus 29 equals 67. Okay, we said we have 60 seconds in a minute, so we can't have a number here over 59 because as soon as you hit 60 seconds, that's going to equal a whole minute. So what we need to do in a case like this is we're going to subtract the 60 seconds out, and that's going to give us 1 extra minute. So we'd go minus 60 equals 7 seconds, And then that's 60 right there. 60 seconds equals 1 minute. So we're gonna add 1 minute up at the top here. We'll do the same thing over here. We'll go 42 plus 28 plus 1 equals 71. 71 minutes. Again, we're over our 59. So we're gonna have to take that full degree out of this one here. So we're gonna go minus 60. We're gonna end up with 11 minutes. Okay, and that 60 minutes turns into a full degree. Now we're gonna go 114 plus 105 plus 1 equals 220 degrees. So our final answer here would be 220 degrees, 11 minutes, and 7 seconds. Okay, so now we're going to subtract decimal degrees, okay, so now we're going to subtract degrees, minutes, and seconds. So let's use a number, let's go 130 degrees, 30 minutes, and 45 seconds. And we'll subtract 45 degrees, 15 minutes, and 23 seconds. Okay, this one here is going to be pretty straightforward. We're just taking our 45 seconds, subtracting our 23 seconds, and we've got 22 seconds. 30 minutes minus 15 minutes is 15 minutes. And if we go low, 130 degrees minus 40 degrees is going to give us 90 degrees. So we'd be 90 degrees, 15 minutes, and 22 seconds. Okay, if we get into a bit of a trickier question where the number on the bottom could be a little bit bigger than the number on the top. Let's say we have a number 142 degrees, 17 minutes, and 14 seconds. And under here we'll go 33 degrees, 50 minutes, and let's say 52 seconds. Okay, we're subtracting here. So we want to go 14 minus 52. Obviously can't take 50 off. Obviously you can't take 52 off of 14. So what we're going to have to do is we're going to have to steal a minute from over here. So we'll be down to 16 minutes, and that's going to be adding, since we're stealing 1 minute from here, that's going to add 60 seconds on this side. So we go 60 plus the 14 would be 74. Okay, so 60. We went 14. Plus the 60 seconds equals our 74 seconds. Then we get the 74 minus 52 equals 22 seconds. Okay, we're going to do the same thing over here now. 16 minus 50, again, we can't do that, so we're going to have to steal a degree. So we're going to subtract 1, so it'll be 141 degrees. We're going to add the 60 minutes to our 16, so we'd be 76 minutes. So it'll be 76 minus 50 is going to be 26 minutes. Okay, and then the last one here, we've got 141 minus 33 equals 108 degrees. So our final answer would be 108 degrees, 26 minutes, and 22 seconds. We're going to take a few minutes here to talk about a coordinate system that we use with the total station in order to lay out buildings. This coordinate system is called northings and eastings. Okay, it works on an axis. So we've got our x-axis being the horizontal and our y-axis. Okay, the x x-axis is east and west. The y-axis is going to be north and south. Okay, anytime we're to the right of the y-axis, we're going to be a positive coordinate. Okay, so our easting over here would be positive. Easting on the left side of the y-axis would be negative. Okay, so when we're talking about the north coordinates, anything above the east and west axis is going to be positive. So our north up here would be positive. Anything below would be negative. So our north down here would be negative. Okay, same thing goes on this side here. If we're below the x-axis, we're going to be negative. And on the top here, we're going to be positive. Now when we're using the total station, what we want to do is we want to always keep our eastings and northings positive. So we're always going to be working out of this quadrant up here. Okay, so now that we determined we're up in the top right hand corner here, we'll draw these grid lines on here. So this will be our x-axis, or our eastings. This one up here will be our y-axis, or our northings. And this intersection down here we call our point of origin. Which is northing 0, and easting would be 0 also. Now these measurements could be in anything. They could be metric, they could be imperial, but for us right now we'll go with imperial. So now that we've determined our point of origin, what we're going to have here is called our point of beginning, or POB, and that will normally be a northing of 1,000. Okay, we'll go with feet for now, and an easting of 5,000 feet. Okay, and the reason we do that is so that you can visually see that we're only 1,000 foot up and 5,000 over, so that we don't get the two numbers confused. From there, we're going to have parallel lines to our point of origin, and all of our layout are going to come off of these lines. These lines here I think of as grid lines, or as a bit of a batter board system. We're going to be using these as to lay our building out originally. We'll have a bit of a building over here. Let's draw a bit of a shape. We do our layout off of these lines here. Once we lay out these points here, you're going to be excavating this whole area. You're going to be losing all those points, and then you're going to have to reset the total station back up on your point of beginning to relocate those points down in the foundation to lay out your footings. Okay, over here you're going to have some sort of an offset. So let's go 100 foot over here. And over here we'll go 100 foot also. Okay, next up we're going to determine our coordinates for this point right here. Now when you're looking at the data collected in the total station, all these points here are going to be numbered. So we'll call this point number 101, point 102, 103, okay, all the way around, so that we know what we're trying to locate, which point we're trying to locate. If we want to figure out what point 101 is, what we're going to do is we're going to start out at our point of beginning. To get to this point here, we're coming up off of our x-axis straight up 100 feet. So our northing coordinate would be 1,100 feet. To get our easting, we're going to be coming off our y-axis. We're coming over that same 100 feet. So our easting measurement, your easting coordinate would be 5,100 feet. Okay, we're just taking that 5,000, which is right here, and we're adding that 100 to it. So to get the rest of the points here, we're going to have dimensions on this building. So to keep the numbers nice and simple, let's call the length of this wall here 50 foot, 50 foot. This one here we can go 60 foot. Across the top here we can go 40 foot. The back here would be 110 foot. And across the bottom here we'd be 90 feet. So if I want to figure out my coordinates for point 102, again we're starting off at the 1,000 here. To get up to that point 102, we're coming up the 100 foot plus another 50 foot. So our northing would be 1,000 plus the 100. So 1,100 plus 50 would be 1,150 feet. So to get our easting coordinate, we're starting off here at, our easting is 5,000 foot, and we're coming over that 100 foot. So our easting coordinate would be 5,100 foot. If we want to figure out 0.5, for our northing, again, we'd be starting off at 1,000. We'd be coming up to 100 plus another 110. So our northing up here would be 1,210 foot. Our easting, we'd be starting at the 1,000, so we'd be coming over 100 foot, the 50 foot, and another 40 foot. So we'd be 5,190 feet. Okay, we can use that process to determine any one of these points. Okay, just know that everything is based off of our point of beginning. Okay, so we'll do one more point here. We'll do point 106. This time I'm going to relate it to a couple other points we have here. So when we're figuring out our northing measurement, we're going off our baseline. We come up to this point here. On this coordinate here, we were northing of 1,100 feet. Because we're still parallel, that northing coordinate doesn't change. So that's still going to be the 1,100 feet. Okay, same goes for our easting. When we came over from our y-axis to locate our easting coordinate for this point 105 up here, we had an easting of 5,190. Because this is parallel to our y-axis, it's going to remain the same, right? We still came over, we started out our 5,000 foot, we added the 100, the 90 foot, so it would be this exact same coordinate as point 105. So easting will be 5,190 feet. One of the advantages of using the total station for layout is the accuracy of the instrument's calculations and measurements. While it's best to avoid human error when calculating distance and elevation, it's still important for the carpenter to understand the math calculated by the total station. The first thing that we will review is Pythagorean theory, and then the basic trigonometry terms of the opposite, adjacent, and angle of interest of a triangle. Next, we will look at how the total station calculates an elevation. So to start off with Pythagoras' theorem, the formula is a squared plus b squared equals c squared. Okay, this only works on a right angle triangle. The concept is one side 3, 4, and we're going to solve for the diagonal. Okay, we would use this when we're laying out foundations on a 90-degree angle wall. So what we do is we just take the formula and we plug these numbers in. Now these two numbers can be interchangeable between A and B, okay, but C always has to be the longest side. C is always your hypotenuse over here, and it's always going to be directly across from your 90-degree angle. So to solve for the letters here, we'll call 3 here, we'll call A, 4 we can call B, and the diagonal here we'll call C. So we'll plug this into the formula. A is 3, so we'll square that, plus B we said is going to be 4, so we'll square that, equals c squared. Okay, next BEDMAS says that we've got to get rid of our exponents, so we'll square these numbers here. 3 squared is 9, plus 4 squared is 16, it can be equal to c squared. Now we can add our two numbers together. 16 plus 9 equals 25. And now we've got to get c all by itself. So the opposite of squaring is square rooting. So anything we do to the right side of the equal sign, we have to do to the left side. So in our calculator, we punch in 25 and find the square root of that. Square root of 25 is 5, so c would equal 5. So when it comes to layout, we could be given a foundation with dimensions, say the diagonal is 25 foot 8 3/4 of an inch. This side here could be 18 foot 8 1/4 inch. And if we want to solve for this other side here, we can use this theorem. We're going to have to rework the formula a little bit, but we can use these numbers to solve for the shorter side. So the formula is going to maintain the same. A squared plus b squared equals c squared. Okay, again over here, we can call the short side A, the longer side B, and the longest side is always going to be your C. So we'll plug those numbers into the formula. A, we're not sure yet. That's what we're going to be solving for. B, we're going to have to convert these to decimal. So 18 foot 8 1/4. Okay, that will be 18.6875 feet. Okay, while I'm doing my conversions, I might as well convert this number here also. So 25 foot, 8 inch, 3/4. So that in a decimal would be 25.7292 feet. Okay, we can punch those into here. So B was our 18.6875 feet equals C we just said was 25.7292 feet. Okay, now what we need to do is to rework the formula. We've got our numbers in there. We want to get a squared all by itself. Since we're adding the 18.6875 to the a squared, the opposite of that is going to be subtracting it. If we subtract from the left side, we've got to subtract from the right side. So on the left side here, we're going to subtract the 18.6875 feet. We're going to have to subtract that same number from this side, 6875 feet. Okay, on the left side, we'll be left with a squared. On the right side, we subtract that 18.6875. We'll be left with 7.0417 feet. Okay, just as before, we want to get rid of that squared. So we're going to be finding the square root of that on the left side. We have to do the square root on the right side. So on the left, we'll be left with a, and we find the square root, 7.0417 is going to be 2.6536 feet. Okay, we can convert that. So we would be 2 foot, 7 and 13/16 of an inch. Okay, so A would be 2 foot, 7 and 13/16. So there's a quick example of how we use Pythagoras to solve for any of the three sides. At any given time, we can be given any two sides of the triangle, and we can use that formula to solve for the third side for layout purposes. Okay, next up, we'll get into the basics of trigonometry. You guys might remember from high school, the acronym SAW, TOA. So the S stands for sine. There's a little symbol for angle. And the O stands for opposite over hypotenuse. Okay, we could use cos. Again, there's a symbol for angle equals adjacent over hypotenuse. And the last one here, we've got TOA, where tan, the angle equals opposite over adjacent. Okay, we're going to use this on right angled triangles. So when we're doing layout, we're going to have to be always given at least two pieces of information. So if we're given a right angled triangle, okay, we'll be given an angle. We can be given the length of a side. So let's say here we'll go 18 foot 6 inch. Let's say the angle inside here is 32 degrees, 14 minutes, and 53 seconds. Okay, now in carpentry, anytime that we're doing trig, we're going to be using the tan. Okay, the reason for that is we're always relating to the sides to our angle. In this angle here, we're given the 32 degree, 14 minutes, and 53 seconds. And we want to relate that to the sides of the triangle. Okay, over here we've got tan, we've got opposite over adjacent. So the opposite is always going to be in relation to the angle here. It's always going to be directly opposite the angle. So this over here would be our opposite. Okay, this side directly beside the angle is going to be our adjacent. And we said it's a right angled triangle. We just were talking about Pythagoras. So this longest side always across from the 90 is going to be your hypotenuse. So this is the formula that we're going to use most in carpentry. Now, depending on the information that we're given, whether we're given the opposite, the adjacent, or the angle, we could have three different possibilities for the formula. The easiest way I find to figure out which one we're going to use is to put this in a triangle, where tan the angle equals opposite over adjacent. Okay, so we have three different options. If we're solving for the angle, we would have tan the angle equals, and we're going to go opposite. This line here is going to represent divide, so we'll be dividing by adjacent. So we'd be opposite over adjacent. Okay, if we're solving for the opposite, we'd put opposite on the left side of the equal sign, opposite equals, and then we've got tan the angle. Over here we'd be multiplying by the adjacent. So opposite equals tan the angle times adjacent. Okay, or the third option would be, if we're solving for the adjacent, we'd be putting the adjacent on the left side, and then we'd be back to our divide. So we'd be opposite divided by tan the angle. So those are the three formulas depending on what information we're giving. Okay, so back to our triangle over here. The next step I would do is to turn these numbers into decimals so that we can punch them into our formulas. So I'll take my 53 seconds, divide by 60, add my 14 minutes, divide by 60 to get it into degrees, and we would be 32.2481 degrees. Okay, this number over here would be 18.5 feet. And now what we need to do is determine which formula we're going to be using to solve for this triangle. We want to solve for opposite. Okay, so we said that opposite equals tan the angle times adjacent, so we'll write down that formula. So opposite equals tan the angle times adjacent. Okay, tan, the angle there is 32.2481 degrees times the adjacent we said was 18.5 feet. Okay, we're going to use the tan function on our scientific calculator. So we'll go 32.2481 tan. The number to come up with is 0.6309 times 18.5 feet. So we're going to multiply that by the 18.5. And we're going to end up with 11.6718 feet. Okay, equals 11 foot 8 and 1/16 of an inch. Okay, so our opposite over here would be 11 foot 8 and 1/16 of an inch. Okay, so we'll use an example. Let's say we have our total station set up and we shoot it across at a wall, and we want to figure out the height of this wall. Okay, we're going to take our instrument and we're going to shoot it down to the bottom of the wall there. We're going to have to be given two pieces of information. So we'll say that we already know that the distance from the wall to the instrument is 56 foot 3 5/8 of an inch. And we want to solve for the height of the wall here. And we're going to use the instrument to figure out what our angle is. Okay, the angle that we're going to need to solve this triangle is going to be inside here. To get that, we have this thing called zenith angle. Okay, zenith is always 0. So straight up, if you were to take that instrument and point it straight up, you'd be 0. So as you come down here, the instrument's going to give you a reading Let's say that this reading here is 105.4289 degrees. Okay, that is the angle from our zenith line here down to this bottom line. But for us to solve for this triangle, we need to get the angle inside the triangle here. So in order to do that, we're going to subtract this 90 degrees off of here. So it'll be the 105.4289 minus 90 degrees. So it would be 9824, and it would be here 15 degrees. Okay, so that'd be the angle inside here. What I like to do is to take this triangle and just to kind of clean it up a little bit is we'll redraw it. So our angle inside here now, we have our 15.4289 degrees. Okay, we can convert our 56 foot 3 and 5/8 to decimal. So 56 foot 3 and 5/8 would be 56.3021. Okay, and this over here we said is going to be our footing. So that's what we're going to be solving for. Okay, the next thing I like to do is to identify the sides of the triangle. We said if this is our angle here, the one directly opposite will be our opposite. The one beside it here will be our adjacent. And the longest one, always directly across from the 90, will be our hypotenuse. Okay, the two pieces of information that we have right now are the angle and our adjacent, but the formula that we're going to be using has to have the opposite also. So again, we're going to be back to our tan equals opposite over adjacent. Okay, now we got to figure out how we're going to rework that formula. We want to solve for opposite. So we'll be using this formula right here. Opposite is on the left, equals tan the angle times adjacent. So start by writing out the formula. Opposite equals tan the angle times adjacent. We'll plug in our numbers. Tan the angle was 15.4289 degrees times the adjacent is 56.3021. Okay, next we're going to use the tan function on our calculator to solve for 15.4289 degrees. And we got 0.276 times our 56.3021. So times 56.3021 equals 15.5387 feet. Do our conversion. We're going to be 15 foot 6 7/16 of an inch. Okay, so the height of our wall here would be the 15 foot 6 7/16 of an inch. So using the information given and our trig formulas, we can punch the information into the formula and solve for the height of our wall. Another layout challenge is circular objects. Therefore, understanding the general concept of radius, diameter, and circumference is going to be critical to being able to laying out these shapes. So just to get familiar with this terminology, we're going to figure out the circumference of a circle. Okay, we'll start with the radius. Let's say we've got the radius of 9 foot. Keep it nice and simple. Okay, the formula for circumference is C equals pi d. Okay, pi is 3.1416. It's a given. So we can plug that number in, 3.1416 times d. So the distance from here to here is our radius. 2 times radius is going to be our diameter. So the distance across the entire circle would be the diameter. So if we've got a 9 foot radius, we can go 9 times 2 is going to be 18 foot diameter. So we'll go times 18 feet. So 3.1416 times 18 equals 56.54 .88 feet would be 56 foot 6 and 9/16 of an inch. So that would be the distance around the circumference, so all the way around the circle. Okay, we would use that number to figure out how far it is around the outside of a shape, or we could take that to the next step and figure out the volume. The total station is an incredibly powerful layout tool. A carpenter who can accurately and productively operate a total station is extremely valuable to our UBC contractors. With this review of our basic math and geometry of how total station operates, you should be ready to begin your course on becoming a competent total station layout person. Once again, I would like to congratulate you on your dedication to training and making the UBC strong and competitive. Work safe.